Hello, my name is Leon Starr, and I would like to welcome my fellow modelers, both old and new, to xtUML Modeling Days 2021. While it's always nice to see familiar faces, this keynote is for those of you who are new to our approach to modeling software systems. My goal in the next 25 minutes is to share just how this powerful methodology can give you a competitive edge in your engineering career. And I'm going to do this by demonstrating what specifically Shlaer-Mellor has done to elevate me to an advantageous position over and over again in a diverse array of complex and exciting technologies, including jet fighters, robotics, medical and scientific devices, battle simulators, real-time image processing, and currently, autonomous vehicles. By the end of this talk, you will see how you can use this methodology to ramp up rapidly on any complex software system and appear 10 times smarter than you actually are. Before diving into the details, let's get clear on what we mean by the term Shlaer-Mellor and Executable UML. Shlaer-Mellor is a methodology originating in the 80s for building formal software system specifications. These specifications are modeled using a well-defined set of execution semantics, synchronization rules, and computation actions. All of these components were built up from existing mathematical and distributed computing theory foundations. On top of all that, Shlaer-Mellor defined a whiteboard-friendly notation for depicting these underlying mechanisms. To appeal to a wider community, though, the Shlaer-Mellor notation was adapted to be conformant with the then-new UML standard, and thus the name changed from Shlaer-Mellor to Executable UML as established in this book. And, depending on what tools you are using and what interpretation of UML you have layered on, you might be calling it xtUML, iUML, or, my personal favorite, xUML. What's important to remember, though, is that while the notation changed, the executable foundations are still 100% Shlaer-Mellor. And as I will demonstrate, it is those underlying mechanisms, not the notation, that makes our approach so powerful. What sets Shlaer-Mellor apart from other methodologies is that the modeling primitives are defined on mathematical foundations such as sets, functions, predicate logic, causality for synchronization, and data flow graphs. This is in contrast to common modeling approaches that intentionally or unintentionally presume an underlying object-oriented design model. Here we see mechanisms that use or disguise pointers or handles, namespaces, inheritance, static classes, threads, and so forth. Just as one example, a Shlaer-Mellor class is defined as both a set definition and an uninstantiated predicate. We never think of it as some sloppy high-level Java class like most other UMLs. It's not surprising since Sally Shlaer, who mentored me with the patience and occasional temperament of Gordon Ramsay, was foremost a mathematician and second, a software engineer. There are some excellent and accessible books that explain how all of this math works. You don't need them to get started, but if you want to look under the hood and up your modeling game, I definitely recommend them. There are a ton of reasons why direct mathematical foundations in a modeling language are important, but I'll give you just 3 for starters. Say more with less. You can boil everything down to basics and build models that reflect the logic and edge cases of your system rather than clever mechanisms and notation necessary to support a particular implementation mindset. Build models that you can execute and evaluate. Math gives you unambiguous results. Using simple rules, far simpler than any programming language you've ever used, you can confirm that your models work. And this forces you to uncover the important details and helps prevent you from deluding yourself into thinking that you've solved a problem that you actually haven't. Solve a problem once and move on. Take any arbitrary system feature. Let's say that you want to, model how a human performs a safe lane change while driving. Rather than create a solution that breaks every time you deploy to a new platform, or there is a change in some aspect of that platform, you can just create a definitive lane change model and then keep generating a variety of correct artifacts over time. Keep in mind that code is not the only output of a model. You can derive an ontology, or a domain-specific language, or a simulation, or a suite of validation tests, for example. Of course, code generation is an important feature of modeling, but I want to focus on boosting your career and turn our attention back to the mind-expanding capabilities of Shlaer-Mellor. In my early days of modeling, I remember expressing my delight at how a certain class model I had built helped me make sense of a complicated problem. And I remember Sally Shlaer commenting, "It's a great mind tool, isn't it?" That particular quote still pops up in my mind every time I build a model that unlocks some cool insight into a system. So let's explore how this works in the context of real projects. During the late 80s, 90s, and 2000s, I worked with Bridgepoint tool vendors to help solve a wide variety of modeling problems of their customers. Sometimes I would be brought in because the client's models were becoming overly complex for some reason, or perhaps modelers weren't sure what details really needed to be modeled. Often the modelers were having a difficult time just getting started. Whatever the problem, it was my job to get everything on the right track. Regardless of the situation, it was a similar routine. Waiting for me to arrive would be this diverse array of career experts in whatever subjects were relevant to the project. They could be PhDs in physics or math, experts in cardiology, real-time image processing, distributed networks, avionics, you name it. And then I would parachute in for a few days or weeks of well-paid consulting. And if that wasn't intimidating enough, for a good part of my career, I was usually the youngest in the crowd. How could I possibly have been able to make a multi-decade career out of this insane activity? Without a powerful analysis and modeling methodology to help me quickly make sense of all the diverse and complex information surrounding me, it would not have been possible. There is a lot to the Shlaer-Mellor method, but there are two mental toolkits that get most of the work done and set you up for success. Get these right, and the rest will be relatively easy. Get them wrong, and well, you're screwed. The first is semantic modeling, which is just a fancy way to say that you need to build a vocabulary. It's really hard to solve problems without one. The other is domain abstraction, which gives you a systematic way to simplify a given problem space by filtering out important but irrelevant details. These two ideas reinforce one another since each layer of abstraction is defined by its own distinct vocabulary. To reason about a complex system, you need a precise and unambiguous vocabulary to describe it. In fact, this is true even for a simple thing like a geometric shape. Consider an ellipse and ask the question, how do you compute its area? You may already know, and if not, your search engine will certainly answer it for you. But let's pretend for a moment that you've never seen an ellipse before and that your internet is broken. At the moment, you don't have enough vocabulary to solve the problem. So we analyze its dimensions and add the terms semi-minor axis and semi-major axis. It turns out that we can now describe the area by multiplying both of these lengths by pi. So with the addition of terminology, we gain understanding and an operation we can perform. Now we extend our vocabulary further to identify the focal points. We compute them using our axes lengths like so. Now we can talk about the eccentricity of our ellipse. As we improve the precision of our vocabulary, we can do more things. So if you want to reason about a system, you need to build up a precise analytic vocabulary along with all the supporting operations as quickly as you can. Of course, ellipses are already well defined and there's no need to analyze them. But I had this interesting experience where a team was working on some geometric algorithms to express the curvature of edges and divisions of a roadway. Thanks to this thing called Euler spirals, they already had pretty solid mathematical vocabulary to solve this problem. As long as we were talking about curvature, they had all the answers. But a question did come up about how to deal with diverging roads. In my role as the resident idiot, I asked how they defined a road. To my shock, the answer was, that's a good question. Since the concept of a road doesn't exist in math, someone needed to define a vocabulary for roadway configurations in the real world to provide structural context to the underlying geometry problem. So I did end up defining the term road, but that was just the start. It wasn't long before I moved on to crosswalks, complex lane configurations, and intersections. To begin building your vocabulary, you generally start by looking at examples, taking detailed notes, reading background documents, and interviewing the local experts. Then you analyze all of this material and boil it down into an initial set of abstractions. These abstractions are in fact set definitions, classes, attributes, and relationships. I often find it helpful to fill out tables corresponding to these elements to verify that I've accounted for everything in a given scenario. When you can't fill out a table for some reason, it forces you to look more closely at the problem and figure out what you missed. Only after you've developed a solid picture of how things work do you start sketching out a model. In the process of building the model, you gather your source examples along with the definitions that you write up. It's never enough to sketch boxes and lines on a model diagram. You have to force yourself to describe your abstractions. If you do, you will quickly discover your mistakes and spotty areas where you need more information. Now that you have a class model, you look at more expansive examples with greater variations to see if you can still account for them. To the extent you can't, you repeat the cycle, improving your model along the way. This is hard work, but it soon pays off. Soon you are able to talk about your subject matter like an expert. Having built my models, I can describe a vehicle approaching and traveling through an intersection with eloquent precision. Here, for example, is how I might describe the activity of turning left at a signalized intersection using modeled terminology. Our vehicle plans on making an inside turn at the upcoming intersection from the innermost signalized entrance lane.
The selected lane permits both a through and an inside turn movement.
After clearing the entrance crosswalk, it must yield at the inside turn encroach to satisfy a single oncoming traffic yield requirement, originating in the reverse conduit of the opposing road segment before approaching the exit crosswalk.
Okay, maybe painfully tedious is a better characterization than eloquence. But a precise vocabulary has its advantages. In the process of modeling, I discovered a lot of interesting patterns. For example, I soon realized that only 3 traversal patterns are necessary to account for all movements through a signalized angular intersection. And I have a vocabulary that is platform independent. It works for any vehicle company, any vehicle, and any version of a vehicle platform. Wow, that's a lot of work. Why not just write code? I get this question a lot, and it's a good question. Well, you do discover a lot of details when you code. And, like executable models, code can be run and verified. But the primary focus of programming isn't about understanding how things in the real world work. It's easy to forget that a large percentage of what you're doing when you code has little to do with studying the rules of a system. Sure, you do incorporate the rules, but that's just what you're doing. The rules are second-class citizens to your design decisions. Whether your system is an ultrasound machine, or a gas chromatograph, or a jet fighter, or a self-driving car, the models put a bright, hot spotlight on the physical or abstract subject matter you need to master to get the right code. Modeling gives you the tools to understand a system in all its magnificent detail much faster by surprise focusing on the system itself. The other key mental toolkit that I mentioned is called domain abstraction. A domain is just some platform-independent subject matter. To give you a sense of what I mean, consider the subject matter of linear algebra. Like any subject matter, it has its own special vocabulary and its own rules and operations. You can use it for a wide variety of applications, not by adding new vocabulary and operations, but by configuring existing elements with your own values. Linear algebra is linear algebra. There is no special linear algebra just for chemistry or for machine learning. Finally, the subject of linear algebra is entirely platform independent. You can deploy it as a cloud service, Python package, library, stack layer, and so forth. But the way you package it doesn't change the underlying rules and concepts. This example domain is already well understood, and there's generally no need to call it out. The trick on a complex system is to quickly identify the not-so-obvious domains necessary to cut through the complexity. When I parachuted into the field of self-driving cars and started modeling a new vocabulary, I had to make sense of the roadway. Intersections, traffic flows, pedestrian crossings, bike lanes, yielding scenarios, and such are complicated enough when you restrict yourself to your own corner of the world on a sunny day. But when you start looking at the crazy variety of traffic signals and road pavement marking patterns in use all over the world in all kinds of weather, it seems like an impossible task. That's where domain abstraction comes in handy. Instead of trying to build an impossibly expansive and detailed vocabulary, I sort the problem out into a number of interlocking domains, each with its own distinct and achievable vocabulary. In this case, I realized that I could separate out the fundamental structures and traffic flows from the problem of decoding surface markings, traffic lights, cones, and so forth. The domain focusing on roadways, intersections, and traffic flows is what I call the vehicle guidance domain. To support that domain, there must be another domain concerned with decoding regional symbology, as well as a domain or two to help identify the positions of street signs, traffic lights, and pavement markings. By establishing the separation of concerns early on, I'm able to work productively in the domain of interest without being distracted by extraneous details. When I say extraneous, I don't mean unimportant. All details are important. It's just that you want to address every detail in the domain where you have the specific vocabulary, rules, and operations appropriate to the task. Equipped with the domain of interest and a set of supporting domains to be modeled later, I can focus without worrying about missing anything important. As new details arise, I sort them into the appropriate domain and keep modeling. In this next example, domain abstraction was key to solving a long-standing problem in the world of modeling tools. A common objection to modeling is that it is difficult to productively and seamlessly integrate model artifacts into configuration management. Program code is, for the most part, organized as sets of individually managed text files. Configuration management is designed around this assumption so that you can diff, update, check in, and perform lots of other operations seamlessly on your code. Models, on the other hand, are often stored in databases, binary files, or serialized as monolithic text files. Even when saved or specified entirely as text, models typically bind model semantics with graphic layout data and other non-model information. This makes it impossible to work with your model components as freely and fluidly in a configuration management environment as you can with your code. A few months ago, I set out to crack this problem using domain abstraction. I knew that the solution involved breaking the model components into separate, easily editable text files. But more importantly, I needed to completely disentangle the graphical layout and diagram notation from the fundamental model semantics. This would ensure that a change to the layout wouldn't be confused with a change to the underlying model itself. Furthermore, I wanted to be in a position where I could support a variety of modeling languages and diagram types. One of the end results would be that I could diff a model file and update it without concern for the layout, or that I could change the layout around without fear of breaking the model. Now, many of us already know that the semantic model of a modeling language is its metamodel. The metamodel of executable UML consists of classes like attribute, identifier, association, generalization, and of course class, among many others. This metamodel is in fact the class model of the executable UML domain, and the purpose of this domain is to make it possible to specify a given executable UML model independent of any particular layout or notation. For example, we may know that there is a one-to-many association between a runway and the aircraft queuing for takeoff, but where the classes are placed with respect to one another on a diagram, and how that line is drawn, and with which notation, is a separate matter. That information is simply not in the metamodel. The metamodel can be used to define one or more DSLs, that is, domain-specific languages, so that you can create a model as a set of text files. Now to specify the layout information, we need an entirely different domain, built from a semantic model of our layout system. To make layout controllable yet simple, we define classes like connector, node, cell, diagram type, and so forth. I'll talk more about these in my Flatland presentation later today. But we can use this model to define yet another DSL for mapping model elements onto a given layout and notational scheme. The 2D graphical entities necessary to do the drawing are in yet another domain that concerns itself with device-specific coordinate systems, drawing surfaces, layers, and fundamental geometric elements. This was defined by implementing a layer on top of an existing 2D draw engine named Cairo. By separating out the domains at the outset, I could focus where it mattered without worrying about the details of the 2D graphics. This means every brain cell was focused on devising a beautiful solution to a layout system for model diagram elements. Since I didn't have a model-to-code Python generator handy, I hand-coded the diagram layout domain from my models. And I can't even begin to tell you how much easier it is to code from models than pulling your requirements and design out of thin, agile air, especially when the concepts get abstract and complex. And the modeling language domain was implemented via the DSLs and associated parsers, along with a small amount of Python to translate the parser output to calls into the diagram layout domain. By the way, you can find all of the models and code for the Flatland model diagram generator on my GitHub site. The end result is that I can keep all my layouts and models under configuration management, just like code files. So I can do a diff and a global replace on the model without worrying about the layout, or I can experiment with different layout variations without a risk of accidentally breaking my model. You probably noticed that these two mental toolkits, semantic modeling and domain abstraction, reinforce one another. In fact, it's difficult to limit yourself to one without doing the other. The semantic modeling shores up the domain definition and makes it a real thing. The domain abstraction breaks complexity apart so that you can focus and find good solutions. Now I want to take you on a journey through logic. Don't worry too much about understanding the application, though I have chosen one that you are somewhat familiar with. I do make some arbitrary definitions, but that's what we do in logic. We start with axioms and build our way up to proofs. So I want you to see how the process of modeling your vocabulary is, in fact, a process of modeling logic. Let's start with the road segment. We say that a road segment has a left and a right edge. by definition. Now, each line extending longitudinally down the roadway is going to be considered a lane division. On a completely unpainted road, worst case, there are at least 2 lane divisions marked by the road edges. In a case where we have a shoulder, there could be more lane divisions. We define a lane as the pairing up of adjacent lane divisions. We'll say that any road segment then is partitioned into one or more lanes. We'll come back to lanes later. Let's think about the basic pattern of how lanes direct the flow of traffic within a single road segment. It's helpful to start by looking at a nonsense pattern. Here vehicles are flowing back and forth in the same road segment with an arbitrary direction chosen for each lane. In reality, this sort of thing never happens. In fact, if an autonomous vehicle for some reason thought that it was seeing this sort of thing, the software should immediately recognize that something isn't right. Maybe there's some faulty perception or planning algorithm feeding us bad information. If we can't automatically validate a correct pattern of traffic, we will have no way of recognizing when we are given one that is incorrect. It turns out that there are only 3 flow patterns possible in a road segment, in the real world of driving. And here they are: one-way, two-way, and shared. All lanes flow in the same direction in a one-way road segment. 2 pairs of adjacent lane sets flow in opposing directions in a two-way. And in the case of a shared road segment, road traffic flows in both directions, with vehicles squeezing past each other as necessary. We aren't just taking an ad hoc inventory of every traffic flow we've seen. We're using a bit of logic to hypothesize that these must be the only possibilities. And our definition doesn't prevent us from identifying interesting combinations like a one-way road closely parallel to a two-way road. For this presentation, though, let's keep the focus on one road segment at a time. And we'll start by modeling a one-way road segment. Here we see a set of adjacent lanes flowing traffic in the same direction. We'll call this set of lanes a conduit, as the term describes a unidirectional flow. On a two-way road segment, we observe that there are 2 conduits moving in opposing directions. Now we could model this as a one-to-many relationship. Two-way road segment flows traffic in n conduits, but that would be incorrect. There can, by definition, only be 2, and they must flow in opposing directions. So we must abstract out the concept of forward and reverse paired conduits. And since both the one-way conduit and the forward and reversed conduits share a similar definition, we abstract a superclass called conduit. Okay, here comes the fun part of the logic. How do lanes and conduits relate to one another? You might be thinking we just model a one-to-many association between lane and conduit. A conduit requires at least one lane to define a flow of traffic. But does a lane necessarily need to flow traffic in a conduit? Before you answer that, let's consider that third type of road segment, shared. In a shared road segment, the vehicles just squeeze by each other. There is no uniform flow of traffic and hence no conduit. But we decreed that a minimal road segment must have a right and left edge boundary and hence a single lane. Therefore, a lane in a shared road segment is not part of a conduit, and so not every lane flows traffic in a conduit. To resolve the problem, we observe that a lane is either unidirectional or bidirectional. And now we can say with confidence that every unidirectional lane must be part of a conduit, and that a conduit consists only of unidirectional lanes. This then leads us to wonder where we might find bidirectional lanes. Well, the shared single-lane road example is the easy case. But our model has raised the question of whether or not there's another possibility. Turns out, at least in the USA, there is. It's the center turn lane, often referred to as the suicide lane. My wife is Swedish, and she does not like them. So not only are we modeling logic, but our logic, as it so often does, leads us on a path directly to our edge cases. And quick mastery of the edge cases will help distinguish you as an expert. So what has Shlaer-Mellor ever done for me? Well, what we really care about is what can it do for you? It provides you with techniques to model complex data, sort that data into distinct layers of abstraction, and, thanks to the executability of the modeling language, guides you to a detailed understanding of how a system works with all its many edge cases. Throughout my career, I have relied on these techniques to rapidly ascend from idiot to acknowledged expert in a wide variety of applications. More importantly, I've seen the same effect play out on fellow team members who have invested the time to apply those same mental toolkits. I can name more than one project where I've seen previously unrecognized talent catapulted rapidly into leadership positions. So yeah, I'm going to give this methodology 5 stars. Before you can put the mental toolkits of Shlaer-Mellor to use, you need to ramp up on them first. Like chess, It's deceptively easy to get started, but takes time and practice to develop your idioms and strategies. So if you're looking for a quick hack for your career, this is definitely not it. Like any subject you've learned in school, it's going to take time to learn and apply. Therefore, I recommend you get started immediately. So how do you learn this stuff? Well, you pretty much learn it the same way you learn a programming language. Based on my experience, there are at least 4 things you need to do. You can't get good at anything without routine, hands-on experience. That means you need to start applying the mental toolkits on a project, no matter how small, right away. And when you're done with that, get going on another one. Ideally, you would like to apply Shlaer-Mellor to a project that is currently paying your bills. Depending on the project, that can be difficult to impossible. But often just doing a simple domain abstraction and sketching a few models may lead to some useful enlightenment on your current job. Failing that, just go build your own thing on your own time as a weird little hobby. Reverse engineering is a good approach because the requirements are already known and fixed. You just need to build the models. Choose a board or video game or some app you like and just go model it. You don't have to build the whole thing, choose some subset of the functionality. Eventually, you will have something to show for your efforts and have enough basic skill to apply these techniques on a real project. Ideally, you would like to get paid, but until then, you can get some recognition by contributing to an open source modeling project. Be persistent. Modeling and systems analysis is not for the faint of heart. It is hard work. So don't be discouraged if you get stuck and confused a lot. That's how you know that you are stretching your limits and learning. So never give up, never surrender. Unfortunately, we're not big on Stack Overflow yet, but you can always ask for help via the Shlaer-Mellor Commons or the discussion boards on my GitHub project sites. Get comfortable with the tools that help you get the job done. The Shlaer-Mellor Commons defines 3 primary flavors or camps of executable UML, and each specifies its preferred tooling. I work within the xUML model integration/realization camp, but the others are certainly worth exploring. The book, Models to Code, explains our camp's approach to tooling in great detail. Read, read, read. Anything you can get your hands on. And don't just read once. After you've modeled for a bit, stuff you glossed over in the past will pop to the foreground and take on new significance. I've read those 2 books on the right, cover to cover, at least 10 times. It's pretty difficult to find me on social media, but here are a few breadcrumbs that might help. To stay up to date on all of my activities, join the Executable UML LinkedIn group and follow me on Twitter. Projects, wikis, and discussion boards are on my GitHub site. I don't have anything yet on my Instagram or Medium site, but I have plans for the coming year. I have some papers and videos on the Model Integration website, and there's a dedicated site for our Models to Code book. And of course, there's email. Okay, that's all I've got. If you find yourself lured into this weird world of Shlaer-Mellor and executable UML, feel free to reach out via any of these channels, and I'll do my best to help. Thanks for watching.